Hello there. Can you guys hear me?
Yes, but I can't see you.
Yeah, you're not going to be seeing me. So you're going to be seeing my screen. Just give me a second.
Hey, you get a free day of not having to strategically clean out your wardrobe.
Yes, that again. I do. Felix, can you hear me?
Yep.
All right, sounds good. Okay, it should be recording, so just be aware.
And the screen is showing.
Okay, excellent. Now, give me just a moment here. Actually, I don't think I need that. I think I need to go under my files. Oh, that's not cool. Summer 2022. There we go. Okay. What are we on? Lecture 9? Yeah. They just finished the work, so I'm very excited. It's all done. Okay, so we did a bunch of vector stuff, and we did distance line to a point, and then we left off, I think, before intersection of lines, right? Okay, so we're going to back it up just a wee bit. Let's make sure it is still recording. Everything's good. Yeah, it's still recording. Okay. All right. Contrary to our popular belief, apparently no one but you two are showing up here either. That's okay though. But this will be recorded. I will upload it to YouTube on a private unlisted listing, and then just share the link on Canvas. So we should be good with that. As a rather quick review up to, let me see, what are we on, about 23? Okay, so quick review about what we did on Tuesday. So we started talking about the need for computational geometry and how it's important to multiple disciplines, and how graphics in general depend heavily on computational geometry, which is also heavily entwined with linear algebra. And we talked about how the graphics have changed significantly over the years. So vectors are what we started with. This is our concept that it has both a direction and a magnitude. And we talked about how to take 2 points and obtain a vector from them. And basically you just do a component-wise difference, and then that yields the vector. And often the vector will, as mentioned, have more something like this instead, using angle braces to indicate it's a vector and not just a point, but it's still sometimes just the point as well, or just the parentheses as well. Okay, give it a second. This is acting funny. There we go. All right, so we also talked about magnitude of a vector. So this is basically just Euclidean distance formula, as we've expected. You take the x and the y component, square them, and then take their square root to get the magnitude of the vector. In other words, how large is the vector, how profound is the vector, how big is the vector, what is its magnitude. So we generally, when we graph it, it would be indicated by the length of the vector starting at, typically we translate it to the origin, and then we would take it out at a particular degree and at a particular length, and that length would be the magnitude. And also, it is common to pull out squares. So since 20 is made up of a perfect square here and a thing that is not a perfect square, you can pull that perfect square out by taking its square root. All right, so we did sum of vectors also. It's a component-wise addition in this case. So we did that. We talked about dot product and how you can obtain the angle theta between them. And as a result of the trigonometry that ensues, the dot product, if the dot product of 2 vectors is 0, then that means they are perpendicular, or rather at a 90 degree or pi over 2 angle between the 2 things. And then we talked about cross product. This is actually what we do a little bit more. And to find the magnitude of the cross product, it's actually fairly simple. The magnitude is a scalar value. The magnitude of the cross product is the x component from the first operand multiplied by the y component of the second operand vector minus the y component of the first operand vector times the x component of the second operand vector. So the order does indeed, in most general case, matter. Okay, so we talked about that. Then we talked about algorithms, started to talk about algorithms in computational geometry, and that's kind of where we found ourselves last time. All right. So algorithms in computational geometry, we've got distance from a line to a point. We started talking about that. And in order to find that distance from a point C to the line AB, which is the line itself, the C being the point that's not on the line, that vector. So AC, the AB by AC magnitude over just the magnitude of vector AB, which are the component points of the line, is how we calculate the distance to a point. So there's actually multiple steps. Typically, or sometimes you might be given maybe 3 points in total. So here I gave explicit points, but it's much more likely, as we went over last time, that you would get the equation of a line, such as y equals mx plus b. And in this particular case, you can see pretty easily that in order to find 2 points on the line, because that's ultimately what we need in order to get our vector, we can just usually plug in just a 0 and a 1. That's the easiest way to go, but you technically could plug in any numbers. So that should make it pretty doable, pretty straightforward to find the appropriate points so that you can then do what we did in the previous example, which was find the vectors from 2 points. So here we just found the points, the 0, 4, and the 1, 6, and we were already given this 4, 1, which is our C value, because that's the point not on the line. So the following points, we have the points, and then we had to find these corresponding vectors AB and AC because they're the only two used in this particular formula here. So you don't need to calculate things like, every permutation of every vector that could make up this entire scenario. Like you don't need BA or BC or any of that. You just need AB and AC. So the point from which it goes to the point it's headed, and then you can find that vector right here with the component-wise difference. So you have 1 and 2 here, and then 4 and -3 there. And then we went on to say that once you have those, then you can start working with the formulas we learned for the magnitudes. So the easier of the two would be, of course, the magnitude of the AB, the single vector AB, and you just do Euclidean distance here, and that's √5. And then we used the formula for magnitude of the cross product. So x1 y2 minus y1 x2, and we discovered this is in fact 11. And then of course you just combine them because we have the formula here now, and we have the two parts of this formula. So you get 11 over √5, and then if you rationalize the denominator, you get 11 √5 over 5. All right. Okay, any questions before we move on to intersections of lines, or intersection of lines rather? Nope. Okay. So finding the intersection of a line with another line. So this time we're dealing with 2 lines. We want both of the linear equations in this form. Okay, so this particular type of standard form. So instead of the more like the slope intercept form, we've got this form right here, ax plus by equals c. So once that's obtained in that form, you can then calculate the intersection point x, y thusly. So the x ends up being cross product c times b over a times b, and then a times c over a times b. Okay, so you have to pay very close attention. What are the coefficients? Okay, so let's figure this out. Let's say we're given 2 lines here. These just happen to be in the form we need them. because they're already in the ax plus by equals c form. So we can just get those values. The first one is the a1 is 1 because it's implicitly in front of the x here. And then we have the b1, which is the 2 in front of the y, and then c1 is the 3. We also get the corresponding a2, b2, and c2 in front of here. So a2 is the 3, b2 ends up being the 1 that's in front of this y here, and then the c2 is a 2. When we construct the vectors as a is the a1, a2, so a1 right here, a2, which is right there, so that's 1, 3. And then we also have b equals b1, b2. So b1 is 2, b2 is 1. So these actually end up being kind of the x, ultimately the x, y values of our intersection point is what they're really boiling down to. And then the c value, of course, is the c1 comma c2. We end up with these 3. Now, once we have those 3, what do we do with them? Well, again, these are vectors, not just points, okay? So we have the cross product, that actually should be magnitude, sorry. There's a magnitude of cross products right here. In order to find the x, y, the point of intersection, we have to find the cross products, magnitude specifically. So we'll just pretend that says magnitude explicitly, but we have x1 times y2 minus y1 times x2. So we take the corresponding components from the, in this case, the 1 are all the a's. So we should have a 1 and then a 3, which we do. So 1 is here and then the 3 is there. And then for the other one, we should have 2, 1 for the b, which we do. So we can multiply those. We get 1 minus 6, and that's -5, right? And then of course we have to get, so that's basically the denominator for both of these right here. Now we need the magnitude of c times b and the magnitude of a times c. So the magnitude of c times b is the x1. In this case, the 1s represent the stuff coming from c, and the b are the 2s. So c should be, the x is 3 and the y is 2. And we do see, in fact, that is the case. The x being the 3, and then the y1 is 2 right here. And then the other one is the b, that's 2, 1. So 2 for the x value, 1 for its y value. You end up with 3 minus 4, which is -1. And then what we do is we calculate the magnitude of AC. So in this case, the A again is the X1 and Y1, which is 1, 3. We do in fact see those right here. And then we have the C value, or the C vector, which is 3 and 2. So we should have a 3 over here and a 2 over there, which we do, a 3 and a 2. So we have 2 minus 9, that ends up yielding -7. So now we've done all that work. Now we just have to get the scalar values for the corresponding X and Y value. So now that we have those cross products, now we solve for X, Y. So you get X equals -1 over -5, which ends up being just 1/5. And then we end up with -7 over -5, which is 7/5. So our intersection point, this time, the point is 1/5, 7/5. And the questions may arise, well, are there other ways of finding the intersection of two lines? The answer is, of course there are. You've learned those in probably basic algebra, right? You can find their intersection in a multitude of ways, especially two equations, two unknowns, do substitution, you could set them equal to one another. There's all kinds of stuff that you could do to try to calculate the intersection points. But in our particular interest is, I'm not as interested in just the answer. I want the solution, and I want that solution to use a linear algebra theoretic or computational geometry theoretic approach. So this is what I'm interested in. So if you see the, for those listening, hopefully you get to this before you take another quiz or test or something that has this stuff on it. I'm hoping that you will note that the problems that you will have when it asks something like find the intersection point of these two lines, I'm not asking you to just give me the basic algebra you learned in middle school. I'm asking you to go through the steps that we're doing here using cross products, okay? Yes, Felix. Yeah, I had mentioned that it actually is supposed to be the magnitude rather than the actual cross product. So it should actually be this. So that's I'll actually now, since I'm on my home computer, I don't have to remember. I'm going to actually let's update that, because that seems to make more sense if we do that. Give it a second. Oh, why it's taking so long to update? Okay. Yeah, give me a second. I will actually re-upload this and replace the current one. So hopefully we can get a little bit more. This is more precise and it's more correct to put it this way. So let's make sure. Did I do it up here? AX plus B.
I think a little higher than there.
Yeah. Okay. Right here. Okay. I'm just making sure I put it. Any instance of it has the correction in it. Making sure. Okay. So okay, that was the previous stuff. So we got the magnitude. Right here. Okay. Okay. Almost up. Let me guess, I probably did a second one with mistakes too, huh? Yes. Great. Okay. No biggie. We will go through that and then we'll do the example. But that could be confusing if someone did not immediately watch the lecture or hear what I said. So we will make sure that this is corrected and updated. Okay. Huh. That's wild that I thought I had corrected this in a previous semester, but I may have forgotten to get the updated copy. Okay.
Also, I think
right.
there's I think there's a slide that's blank.
Down
this
here?
slideshow.
Oh yeah. Okay. Yeah, I'll get rid of that one. Since we're in the area. Okay, let me okay, back it up a little bit. Okay, make sure. That looks good. Nope. Okay. See, we're all about correcting things. This is good. All right. Okay, I think that's a little bit clearer. Let me see here. Do we have it all here? Yes, I believe we're good now. Okay. So now what I'm going to do is I will go onto Canvas real quick here, and we're going to upload. I'm going to replace the current lecture 9 that is there. Not study guides, but then let me do it. As always does. Okay, lectures. There we go. Okay, yes, replace it. Okay. I guess maybe for those that are not in on the meeting or not going to watch the video right away, note correction to lecture 9 slides. The formulae for the intersection of lines has been corrected to use the magnitude of cross products instead of just the cross products themselves. Okay. All right, now everyone gets to know our secrets. Okay. So the equation 2, or example 2 rather, intersection of lines. Captain Picard is telling us to make it so. So we're going to find the intersection of 2 lines. You'll note in this case, they're not both in the form ax plus by equals c. And the order does matter. So you have to use a little bit of your basic algebra skills. I'm fascinated still at the fact that I sometimes teach some more even more advanced classes, and sometimes students will kind of freeze when they see something like this, and because it wasn't something that maybe was gone over explicitly in the class. So that's kind of why I started adding it, because I think a lot of students are very prepared maybe for the actual material that was covered, but they might forget things like, oh, it needs to be in this form for us to grab the AY, or the AB and the C. And they might look at this and say, oh, well, that's 1, 2, 3, so everything's good, because that would be the A, the B, and the C, but they'd be wrong, because the X is the thing that should have the A attached to it, and the Y has the B, and then the constant is the thing that's the C. So we got to make it so the first equation, we can rewrite this as bring the 2x over to the left and the y over to the right. Or actually, I'm sorry, the 2x over to the left and leave the y where it is, leave the 5 on the right is what I meant. So the 2x comes over here by subtracting 2x. So you end up, you have to put it in that order where the x, y, and then the coefficient, or not coefficient, but the constant are off to the right. So they have to be in that order. So that's why I didn't put y minus 2x. So it's got to be negative 2x plus y equals 5. And then the second one is not too far off. It's almost what we need. We just need to make sure that we move the x and the y. We swap places. So it's x plus 2y equals 5. Once we have that, now we can get our a, b, and c for both of these. So the a1 is -2, b1 is 1, c1 is 5. Okay. And then on the other one, we end up with a2 is 1, because that's what's attached to the x. B2 is 2, because that's what's attached to the y as the coefficient. And then C2 is 5. Okay. Therefore, we can then take these as the scalar values that we obtained as the coefficients and constant here. We can just take these values and put them together as the vectors that we need, A, B, and C. So A1, A2 in this case are not vectors, but scalars. So A1, A2 is -2, 1. The B1, B2 is 1, 2, and then C1, C2 is 5, 5. So now we've got our vectors. And then once you have that, it's a little bit smoother sailing. We just now need to figure out what's the, oops, that should go on the, oh, great. So I need to upload that again, because I put it in the wrong place, of course. Let me see here. Okay, I'm going to replace it one more time. Okay. So did I do that anywhere else? Nope, looks okay on the other ones. Okay, so once you have those vectors, you then can calculate the cross products. So the cross products, again, are fairly straightforward. You have x1, y2. In this case, the 1s are coming from the B or the A, and then the 2s are coming from the B. So the A has a -2, 1 for its x and y. So we have -2 and then 1. And then we have, for the B, is the 2. So y, its y value is a 2, as we can see up here. And then its x value, which we have over here, should be a 1, which it is. And then we end up with -4 minus 1. That gives us -5. So we've got that magnitude of cross product. Then we have C times B in this case. So the C times B, you have this time the C actually has the 1s, right? So you should have 5 and 5. So we've got a 5 here and a 5 over there. And then the 2s come from the B. The B is a 1 and a 2. So 1, 2. You end up with 10 minus 5, that's 5. So now we've got both of these cross product magnitude. Okay. So then you have A times C. So we've got A times C, that is x1, y2 minus x1, y1, x2. In this case, because the A comes first, that would account for the 1s. So it should be a -2 and a 1. So you have -2 and a 1. And then you have the x, y coming from the C. So it should be 5, 5, which it is up here. All right. So then we calculate that and get that one. Now, finally, we have all of our, oh, looky here. Wouldn't you know, I did leave one out. This is I'm not scoring very high on this game. Okay, so we will, I guess, upload it once again. Okay. Let's make sure everything looks pretty. Looks nice. Okay, one more time. 3 times is a charm. Okay. There we go. Okay. Now, so we've got, I'm not going to worry about that extra space. That's it. Seems to be finding itself there. Okay. So, why is it doing that? That's weird. Huh, weird. Just angled weird. All right. So the magnitude of the cross products, we have the -5, 5, and 15. And then you just fill them in to find your X and your Y. So C by B is 5 over -5, which is the A by B. That's a -1. And then, of course, you have -15 for the A times C, which that should be there. And then the -15 over the -5, which is the A by B. That's the -5 right there. So that yields a 3. So all of that work is to say we have a -1 and a 3 right here, and that is our intersection point. Okay, any questions about that before we do our brief discussion of the surveyor's formula? This one will definitely, all of this will very likely, most of these things will be on the definitely test 2 and definitely final. Definitely test 2 because it covers the second half, and a lot of these are kind of the more fun things. Definitely be aware of that. And also the surveyor's formula is actually, if I remember correctly, I think I'm having it as kind of a high point value question somewhere in the test. I think both the final and the test 2. So that should be something to keep in mind. Make sure you're comfortable with what we're about to discuss with the surveyor's formula. But so we've got line, point to a line, distance. We've also discussed line intersections and how to use the linear algebra theoretic or computational geometry theoretic or approach to finding these instead of using more of the standard formulas. And truth be told, although for humans, a lot of these other formulas might seem, very, very straightforward. Like I just have to move some of the numbers around and then get the, find the intersection point or do substitution or things like that. For a computer, it might in many circumstances actually be quicker. If you have 2 equations of lines, it can just very quickly look at coefficients and then just calculate the vectors very quickly and then do a couple multiplications and then it's done. So it doesn't take as much creativity, which computers are inherently they're not creative like humans are. So it actually is quite straightforward for a computer. All right, so polygons are up next. So a polygon is any 2-dimensional closed figure whose boundary is composed of non-intersecting segments. Okay, so a convex polygon. So we have convex and simple polygons. So convex polygon and then we have concave polygons. So convex polygon is any polygon in which any contained line segment connecting 2 interior points lays entirely inside the polygon. So for example, in this example on the side here, this is from the book, from the Ellenbogen and Baugh book. B and C are convex polygons, but A is not. A is concave. The reason we know this is if you go to any 2 points inside B or C, any 2 points, and you connect the line between them, it never intersects. It doesn't intersect any of the edges of the polygon or anything else. It's entirely contained inside the polygon. But if you can find any counterexample, then it is not a convex polygon. This one is actually quite simple. Now, there are lines that lay in here that don't cross an edge, that are entirely contained in here. But we have a counterexample here. We could see that if you have a point over here and then a point over there, those 2 points lay inside this polygon. But if you draw a line between them, the entire line does not lay entirely inside the polygon. So in that respect, it cannot be convex. Okay, so it's got a concavity to it. Cavity, concavity, cavity, and cave have the same root word. So cave, you can think of a cave as being kind of like if this were a cliff, there's stuff going into it. Okay, and then over here, we have simple polygons. Simple polygons, a closed polygonal chain of line segments that don't cross one another. So this one over here, this is not convex. It is a concave polygon, the one on the left, but none of these edges cross each other. This one, in the other hand, is not a simple polygon because you have edges that are crossing one another like that. So this ends up being actually, if we were to actually want to construct this in a computer, just as kind of a side note, you would actually have, this would be like a triangle list. So it would have like a point there, 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 or a triangle fan, because they have shared points here and there. You could store it with slightly less memory because it's redundant to store 1, 2, 3, and then 1, 2, 3, and then 1, 2, 3, because you're storing these 2 points twice each when you don't really need to. So you could actually store just the shared point and create this, what we would call a triangle fan data structure. And that would take up a little less memory. But in general, the simple ones are simpler to store. They only consist of one general shape represented by different points rather than potentially technically multiple intersecting polygons. The Surveyor's formula. Actually, we have simplified versions of the Surveyor's formula, which you already know. Area of a triangle, as an example, is 1/2 base times height, and that actually comes from the more general Surveyor's formula. So the Surveyor's formula can be used to find the area of any polygon. It's also called the, I believe, the shoelace formula. Given a polygon with n vertices, so the vertices in this case, these would be the, each individual vertex would be a point that are connected to form line segments that create the overall polygon. Given a polygon with n vertices, x1, y1, we know that setting I equal to 0 all the way through n, arranged in counterclockwise order, so that does matter actually, with x naught and y naught equal to x to the n, y to the n, meaning it has to be a closed figure for it to be to work with the Surveyor's formula. So you have to start and end with the same sub value here. N equals the point x sub 0, y sub 0 should equal the x sub naught, y sub naught. Anyway, the area in this case is going to be this formula here. So you have 1/2 times the sum from 0 to n minus 1 of the x sub I, comma, y sub I times the x sub I plus 1, y sub I plus 1. To make this a little bit more realistic, we're going to use an example. So in this case, triangles are the easiest because you actually don't worry too much about the counterclockwise arrangement. If you get a negative result, you just take the absolute value of it for the three-point situation. For other situations, like with 4 or more points especially, you really have to know where those points are on a graph to know, like, are they counterclockwise, because that's the order you have to take them in. So given these vertices, so in this case, you've got vertices 1, 1, 1, 5, and 5, 3. It's asking to find the area of that polygon, in this case, the triangle, using the Surveyor's formula. So area equals 1/2. I'm going to zoom in just a little bit here because it's kind of small. Area equals 1/2 of the sum from 0 to n minus 1 of the x sub I, y sub I times the x sub I plus 1, y sub I plus 1. So what that does is we're taking these original vertices here, and we have a by b plus b by c plus c by a, right? So that's actually connecting it to the original value. So we have to find these cross products indicated by these vertices, or the I did it again, didn't I? That needs the lines again. Well, that's kind of upsetting, isn't it? Did I put it over here? Cross product. I guess magnitude of cross products really, but I'll leave that. Let me. Yeah, I'll clean it up later. Okay. All right. So these will also be the magnitudes of cross products again, not just cross products. So we do need the cross products. In this case, we've got the vertices A equals 1, 1, B equals 1, 5, and C equals 5, 3. And we know that our formula has to look like this. So we need first A by B cross product, then B by C, and then C by A. And remember, this order does make a difference. So C by A is not necessarily going to yield the same as A by C. So cross products, we have A by B, the magnitude of this cross product using our formula from before. We end up with 1 times 5 because with the 1 times 5 minus 1 times 1 from the A and the B. You end up with 5 minus 1, that's 4. And then you end up with B by C. So that is 1 by 3. We know that the X value, the 1 values are coming from B, which should be 1, 5, right? And then the X2, Y2 should be 5, 3. Okay, good. So you end up with 3 minus 25. So that's negative 22. And then we have C by A. So C, again, is 5, 3. So 5, 3. And then the A is the 1 and 1. Okay, so you end up with 5 minus 3, and that's 2. So we got those values. And then once we do that, we just plug them into this nice little formula here. I have 1/2 times, and then I have 4 plus a negative 22 plus 2. So that should be negative 18 plus 2, negative 16. So negative 16. And then 1/2 of that is negative 8. Now, what I said before was if it was a triangle and you ended up going in the wrong order, in other words, the clockwise order, instead of counterclockwise, you'll get a negative number. And then all you have to do is flip it. So we're flipping this one. Typically, we'd want to know what order they go in. But this tells us that the area of this polygon is 8. All right, so what do we need to know as far as the test is concerned? So as far as the test is concerned, you need to, here, that's better. Okay, so as far as the test is concerned, you need to know the basics of vectors, how to find them when you're given just points. You need to also know how to find the sum and cross products of vectors. I'm not really testing you on the dot product. That's more of a trigonometry thing, and I figured there was enough other stuff to keep you occupied with. So know how to find the sum of the vectors and the cross product of the vectors. So you do need to know those, specifically magnitude of cross products is what I'm interested in. Know the following algorithms or formulas from our computational geometry equations that we discussed. So I could give you a point and the equation of any line, and you should be able to tell me the distance between the point and the line. You need to also be able to find the intersection point of lines, and remember that we want it in this standard form instead of slope-intercept form. And then also be able to use the Surveyor's formula. Know what counterclockwise means and how to calculate using the Surveyor's formula. So obviously, nowadays it's a little more challenging because there's fewer and fewer students every year that are incredibly familiar with an analog clock. But counterclockwise means it's going kind of on the circle this way. If you kind of circle through the points, and it goes through kind of, if you were looking at the top, it would be going to the right. That's clockwise. So you need to look at the points on whatever this, whatever the polygon is. You need to look at each of the points and follow them in counterclockwise order. So if I had something like, give me a second here. Come on now. This is really, really being obnoxious today. This thing is usually very, very fast. I don't know what it's doing. Okay, so this one, if I had like a bunch of points, okay, and we have a polygon here, right? Then it doesn't really matter which one you start with. Let's say we start with this one and label it A. Then I would go this way because that's counterclockwise, right? To get the point. So I'd have A and then B, C, D, E. It really doesn't matter what their names are as long as you do the equation correct. So you want A, B, C, D, E. That's counterclockwise, right? Starting at a particular point. If you started here, that would be fine too, but you still have to go counterclockwise to get the formula correct, right? And then obviously there's kind of the this situation when you have a triangle, it should actually kind of make sense because you end up with 1/2 ultimately. In more of a vector format, you end up with 1/2 BH though, right? So that's kind of, a lot of this stuff is derived from the Surveyor's formula, a lot of the common formula calculations that we have. Okay. What else? I think that's it. All right. Are there any questions, comments, snide remarks? Man, you guys got out really lucky today. And you don't even have to drive. Isn't that exciting? Okay. Unless
You also get the advantage of not having to
yeah.
carefully plan out your wardrobe.
Yes, I didn't have to plan out my wardrobe. I'm sitting here wearing a unicorn suit. That's what I'm wearing. Anyway, yes, Felix, any questions?
I will have questions. I don't have it just yet, though.
Okay. All right. I think that should be good then. What I'm going to do is I'm going to just stop the recording right now. And then we will call it a day because that's it. All right, stop recording.